let's start with what is due this week, and I'm just talking lecture, not lab. On Sunday is the Chapter 2 homework questions, 15 homework questions, just like you saw for the Chapter 1, very similar. We only have one assignment for Chapter 2 though. So Chapter 1, we split it into 3 sections. We spent a lot of time on it because that was our base. Okay, we were learning the conversions, we were learning significant figures, scientific notation, all this stuff that we're going to be bringing into all the other chapters during the semester. So we spent a lot of time on Chapter 1. Chapter 2 is shorter. It's only going to take us 1 week to go through it. So there's only one homework assignment for it, and then the discussion is going to be on any topics from Chapter 2. So anyone you want to pick, you can talk about an atom, you can talk about nuclide symbols, isotopes, electron configuration, anything in Chapter 2. So in the week 4 folder, you'll find the 2 PowerPoints with voiceover posted. So that's where you'll get a lot of these definitions. So I'm gonna talk about the definitions, gloss over it, but I'm gonna focus on the calculation portion during class. So if you want more detailed description of the definitions or of the structure of an atom, you'll find that on the PowerPoints. So it is split into 2 sections. So what we're covering today is part 1 PowerPoint calculations, and then on Thursday I'll post a video with part 2 PowerPoint calculations. Okay, so the video from today will be up sometime today, maybe tonight, maybe the afternoon, depends where I can find the time to get it up. So with that, let's go ahead and start. All right, so
What I'm looking at this word isotope.
what's that?
Isotope, am I saying it right?
Isotopes, yes.
Yeah. Ions. Did we talk about that in chemistry?
Yes, we're going to talk about ions, but that's going to be the second half of this chapter. So isotopes are different, and I'll talk about isotopes in a minute. I want to talk about the structure of an atom first because it'll help explain exactly what an isotope is.
Good, it's my homework question. And
So-
anatomy.
Oh, see, it all comes
All
together,
comes
right? That's why you got to learn
together,
chemistry. It's part of anatomy as well, and physiology. For the structure of an atom, so this is like it's just one representation of an atom. So there's several different ways that people represent and draw atoms. This is a simplified version of it. So I'm just trying to show where the 3 subatomic particles that are present in an atom are. Okay, so the 3 subatomic particles that you'll see are protons, neutrons, and electrons. So we call them subatomic because they're part of an atom. So protons and neutrons. So I represent them with a P+ sign and an N0 sign. This is because of their charges. Okay, protons have a +1 charge. Neutrons, since their name, neutral, 0 charge. Okay, so that's why they're represented by a P+ and an N0. So protons and neutrons, notice I have them in this center circle. So what this center circle is called the nucleus. Okay, so both protons and neutrons are located in the nucleus. Center of the atom. The electrons, the other subatomic particle, represented by an E- sign because it has a -1 charge, the electrons are all these red dots surrounding that nucleus. Okay, so let's look at the charges closely here. We have protons with a +1 charge, neutrons with a 0 charge. And I said they're both in the nucleus, in the center of the atom. So what charge do you think the nucleus has then, if it's got pluses and neutral? It's going to have an overall positive charge. So this nucleus is like a big plus sign. So the reason that we have electrons around it, and what these electrons are doing is they're actually orbiting. So they're constantly moving. It's hard to pinpoint an electron because they're always in motion. They're orbiting this positive center. And the reason they're doing that is because opposites attract. So we have this positive center, and then we have these negatively charged electrons orbiting it because they're attracted to that center. Okay, so that's what holds the atom together, are those opposite charges, that attraction. Okay, so with these charges, what else we need to know about the subatomic particles is their masses. Okay, so in the center, we said we had the protons and the neutrons, so overall positive charge. The center is where all the mass, or most of the mass of the atom is located, Because if you look at the masses, following it down to this next column here, protons and neutrons both have a mass of 1. Okay? And we round this up to 1 because when we calculate, we're going to eventually calculate the mass number using those values there. So most of the density, most of the mass is located here. Now electrons, notice I put a mass of 0. If you look at the PowerPoints, electrons do have a mass, but it's so small that we just say it's 0. Okay, it's negligible. So they have barely any mass. So when we calculate mass of an atom, we don't take into account the mass of the electrons because it's so little. We just look at how many protons it has and how many neutrons it has to calculate mass. And we're going to be doing calculations for mass. So when we do those calculations, you can even write this equation down, it's just the protons plus the neutrons. So no electrons at all. So if you are given all 3 subatomic particles, do not take into account the electrons for mass. If, however, we are looking for charge, in that case, we're going to look at protons and electrons. For charge, we're not going to look at neutrons though, because neutrons, they don't contribute anything to charge. Just the protons and electrons. So the takeaway with these subatomic particles is you want to know the charges of each, and you want to know the masses of each. So that if I'm asking you about charge, or if I'm asking you about mass, you know which particles to look at. Okay? So with this information, we're going to define what an isotope is. So what an isotope is, it's an atom of the same element with different mass numbers. Okay, so for instance, hydrogen. So if you look at your periodic table, hydrogen is the first element on the periodic table. Okay, hydrogen has more than one isotope. What that means is it has more than one atom with different mass numbers. Okay, so hydrogen, it's the first element I said on the periodic table, number 1. All atoms of hydrogen have 1 proton. Okay, all the time, no matter what. But their masses can differ. So you might see hydrogen with a mass of 1. You might see another hydrogen atom with a mass of 2, another hydrogen atom with a mass of 3. However, all those 3 hydrogen atoms will have just 1 proton. The protons always remain the same for the element you're talking about. If you change the number of protons, you are changing the identity of that element. For instance, if I say, okay, the element now has 2 protons. Well, I'm not talking about hydrogen anymore, because I just changed the number of protons. What I'm talking about is the second element on the periodic table, helium. So these numbers in blue, and I know for the virtual people you can't see the periodic table that I'm pointing to, but the numbers in blue, that's the number of protons of every element on the periodic table. Okay, so I'm looking at the top numbers for each element symbol for the people at home. What can change is the number of neutrons. And when the neutrons change, notice neutrons are part of the mass number, so if the neutrons change, the mass number is changing. So that's what an isotope is. It's when the neutrons change affecting the mass number. So we're going to use this knowledge to represent isotopes in 2 different ways, and we're also going to use this knowledge to calculate the 3 subatomic particles if we are given an isotope. So let's see how that looks. So I just said there are 2 different ways to represent isotopes. One is with a nuclide symbol, and the other is to write the element name with a dash and then the mass number. So let's look at nuclide symbol. I'll write 2 examples over here so you can see what that looks like. So this is a basic outline of it. So X is the element symbol itself, straight off the periodic table. In the upper left-hand corner, you're going to write the mass number, and then in the lower left, that's where the number of protons is going to be. So 2 nuclide symbols. One would be bromine 79 and bromine 81. So these are 2 isotopes of bromine. How do I know they're isotopes? Well, because they are atoms of the same element, both bromine, but their mass numbers represented up here are different. Okay? Now notice I didn't put anything in this bottom corner because that's where the number of protons would go. Oftentimes, when you are given isotopes, that number is omitted because if you know what element you're talking about, you can figure out the number of protons, because that never changes. How do you figure it out? You look up bromine on the periodic table. What number is bromine? It's in group 17.
Say that again?
What number is bromine? It's in group 17. 35. So 35, that's how many protons it has. So if you know the number it is, you know the number of protons. So a lot of times it's not put here just because you can find that on your own. If it is put here, it would be 35 on both isotopes of bromine, because if you change the number of protons, it's no longer going to be bromine.
Where did you get those other ones from?
This would be given to you.
Yeah, I got that. I see that one. 79.
The 79 and the 81, those are two isotopes of bromine. You would have to look up, you would have to look up a list of isotopes to know that. So this is something that would be given to you. You would not be able to figure that out from the periodic table. No, not at all. So there's a huge list. So every element on the periodic table has isotopes.
Okay.
So it has different atoms with different mass numbers, and they have a certain percent abundance. So what that means is there might be more bromine 79s than there are bromine 81s. And that would just be figured out by scientists taking a sample of bromine and figuring out what percentage.
They all have the same atomic
They all
number?
have the same atomic number, which is the number of protons. Yes, so 35 all the time for bromine, no matter what. That's not going to change. So given nuclide symbols, a question that you might be asked, or what you might be asked to figure out are, okay, well, how many protons, neutrons, and electrons are in each of these? So just given that symbol, you should be able to figure out all three subatomic particles and their values. So the protons, that's the easy part, right? Because that's the part that's not going to change between the two. That's the part you can look at the periodic table and figure out. So how many protons do each of these isotopes have? 35. It's the same as the atomic number. So 35 for each of these. Now the neutrons. So to figure out the neutrons, we're using this equation. Because this number, 81, and then this number, 79, those are the mass numbers. So we know the mass number, and we know the protons. So we know this guy and this guy. And we're trying to figure out the neutrons. So what do we have to do to figure out the neutrons? Subtract. Yeah, you're taking the mass number, and you're subtracting the protons. And the nice thing about nuclide symbol is it's set up perfectly for you to do that. Right? You put a line here and a subtraction sign. 79, the mass number, subtract the protons, 35, and you have the neutrons.
44.
This guy's 44. So this would be 46. Okay. So subtracting those give. Now notice, protons are the same for both. It's the neutrons that differ. That's the key with isotopes. They have different number of neutrons. Now for the electrons, so now we're looking at charge. Okay. So how do you figure out the electrons? Well, we haven't talked about ions yet, but if these were ions, what that means is if they had a charge, it would show in this upper right-hand corner. So there would be either a plus sign or a minus sign up here. There isn't one. So what does that mean? It means that this compound, or these elements, these atoms, are neutral. Spell neutral wrong all the time. So neutral means they don't have a charge. So if an atom is neutral, that means that its protons are equal to its electrons. How do I know that? Well, because the pluses and minuses have to be the same to cancel each other out and make it an overall zero charge. So if you see no charge here, you can assume that the protons are equal to the electrons. So if you know the protons, you know the electrons.
So basically the electrons is 35?
Electrons are going to be 35 for both, yes.
Okay, wait a minute. Protons is, on this paper is called what?
The atomic number. Protons is called the atomic number. And they are used interchangeably, so know both terms. If someone asks for protons, what they're asking for is the atomic number. If someone asks for atomic number, what they're asking for is the protons. So what I have written over here now is the other way to represent an isotope. So this is just one way. These were the nuclide symbol forms. It's not always written this way. Sometimes isotopes are written with the element name, dash, and then the number that comes after the dash is the mass number. So what we're going to do with the two examples I have written here is we're going to do the same thing. We're going to figure out the protons, neutrons, and electrons, but we're also going to write the nuclide symbol. So we can now practice transforming this into this. All right. So we'll start with iron 57. So let's start by writing the nuclide symbol. So, how do you write the nuclide symbol? Well, you need to know what the symbol for iron is, so you'd have to find iron on the periodic table. And then you would write the mass number, which is given to you after this dash. So, what number is iron? What was that?
I can't say the word. LANTHAN.
Not sure where you're looking. Iron, so if you're looking at iron on the periodic table, it's actually Fe is the symbol. So it's number 26 in the center here in the transition elements.
Oh.
So you're looking at this guy.
I'm looking at the actual, the 57. You see where 57? No, I'm looking at 50.
Oh,
Yeah, I'm looking at the atomic number. Okay.
oh, lanthanum.
Yeah.
Yeah. So the hard thing is with iron and gold and a few other elements like potassium, the words don't match up with their symbol. So it might take a while to find it. But that's why we're learning about the periodic table today. We're going to look at certain areas, common names, common groups, and practice just finding stuff on it. Because the more you look at it, the easier it'll become. So iron is Fe, Latin for ferrous, I think it's Latin. So not all elements were discovered in the US, so our names don't match up with the original name. So Fe, that's where this X is. So what number is going to go in the upper left-hand corner? Right here.
26.
Not 26, it's the mass number.
55.
It's 57. So the number you're looking at is the average atomic mass. That is different than mass number. So mass number is the number of the isotope. So for instance, you just said 55. So on the periodic table, you have, what is the average atomic mass? 55.85. And up here is 26, right? So notice different representations. This is how it's represented on the periodic table. On the periodic table, we have the number of protons up top, right? In the nuclide symbol, the number of protons is down here instead. So these are different. This number here, blue, this is the average atomic mass. So iron has more than one isotope. So what that means is it has more than one atom, and those atoms have different mass numbers. So there's an iron 57, there's also an iron 55. Okay? These are the mass numbers. These are the total number of protons and neutrons in this particular atom. So how do I get that 55.85? It's the average of these two. So what they do is they take all of the iron 55 atoms and all of the iron 57 atoms. They figure out their percent abundance in nature, and they calculate the average atomic mass of all the atoms of hydrogen. So these are all the atoms of iron, not hydrogen. I don't know what that is. So that's the average atomic mass of all the atoms of iron. How do I get these numbers? These numbers are given to me. I would find these on a table of all the isotopes of iron. So you couldn't find these on your periodic table. You would find it on a different table.
The
This is
57?
the 57,
Correct.
yes.
Okay.
So there's more than one isotope.
Okay.
The number that you see on the periodic table, that's the average of all the isotopes of iron. When we're talking mass number, it'll always be a whole number. When you're talking average atomic mass from the periodic table, you'll notice all of those numbers are decimals because they're an average of all the isotopes. So if we take this isotope and represent it as a nuclide symbol, this is what it would look like. We would have the protons on bottom, so different than the periodic table, and then the mass number on top. And I like to represent isotopes this way because they line up really nice for me to figure out the number of protons, neutrons, and electrons. The protons, that's the part that remains the same. So it doesn't matter which isotope of iron I'm talking about, protons are going to be the same. 26 in this case, it's the atomic number. Now, is this element neutral? Does it have a charge? No, there's no charge there. So what does that mean for my electrons? How many electrons? 26 as well, yes. Now the neutrons is the hard part because you have to subtract, okay? So to do that,
31.
it'd be 31. Okay. I see where you got that now. 57, the mass number, minus the number of protons, 26, will give you 31 neutrons.
How are we telling that neutrals?
How do we what?
Something she just said. The neutral.
How do you tell if it's neutral? If there's a charge here or not.
Okay.
So when we look at ions towards the end of the
Is
chapter,
there anything
you'll
on this?
see like a +2 here.
But it's
or-
not on this paper we have now.
No.
No, okay.
The only thing you will be able to get from the periodic table is the symbol, the number of protons, and the average atomic mass. That's it. Everything else would be given to you in the problem itself.
Okay.
So you would get the mass number in the problem, you would get the charge.
But if it was a number, do we add that then? Would then add, correct?
It depends what the charge is, if it's positive or negative.
Negative, okay.
So if it was a positive, that means it lost electrons.
Okay.
It lost negative charges. If it was a negative, that means it has more electrons. And we'll look at that too when we get into ions. So let's try one more of these, doing that chlorine example that I have down there. So chlorine. So we'll write the nuclide symbol, and then we'll figure out protons, neutrons, and electrons. So, chlorine, what's the symbol for chlorine? What letters represent it? CL.
CL.
Yes. It is a L. I know, it's hard to tell because it's just a line on the periodic table, right? But it is Cl because chlorine, I guess they skipped the H and chose the L for the second letter. So how many protons does it have? What's its atomic number? 17, so that's going to go down here. What's the mass number? For the mass number, you're looking not at the periodic table because that's the average atomic mass. You're looking at the example given. Okay, so it's 37. Because that 35.35 or whatever it is on the periodic table, that's the average of all the isotopes of chlorine. So you always want a whole number here. All right, so protons we just said were 17. That's the easy part. How many electrons? 17 as well. It's neutral, right? There's no charge here, so that means these have to be the same. They're the only two subatomic particles that affect the charge. And then the neutrons, subtract so 20. Okay, are there any questions on isotopes, how to represent them, and how to get the subatomic particle counts?
So basically, would you ever use the bottom number?
The bottom number on the periodic table, I don't think, we won't use that probably until chapter 3 or 4. So for now, that's just your average atomic mass, and that's all you need to know about it. It represents the average of all the isotopes. We'll use it when we calculate molar mass. I can't remember if that's chapter 3 or 4. But okay. So right now we're just focused on the whole numbers, the mass numbers. Right. So with that, let's look at where things are on the periodic table, kind of familiarize ourselves with that. Since people at home can't see the periodic table, I'm going to try to draw an outline of it at least up here while we discuss it, so we can label all of the groups and families and stuff. So, put hydrogen there. Two. And the D block here. Go up to, we have 6. All right.
Is there a particular reason why it stopped at 50, 59, and it dropped to the bottom? You get what I'm saying? Like 59 and 60 above is not inside of this.
Yes, so you're talking about the lanthanides and actinides there. So yes, those are our intertransition elements. They have different properties. We actually won't even talk about those until we get to chapter 9 when we talk about radioactivity. So they cut those guys out because they're so different than everybody else and kind of set them aside. So let's look at, and I'm just going to write the first row here.
But even with them being different, keep writing them. Even with them being different, why you drop down with the 50s and 60s, but then you go back into the periodic table?
Because that's their atomic numbers. That's their number of protons. So they have to keep the numbers given to them. So those atomic numbers, that's the number of protons for the lanthanides and actinides. So they couldn't change those numbers, but their properties are so different that they put them down here.
The properties.
Yes.
So they need different properties.
Because that's what we're going to look at now, is the periodic table is arranged so that similar groups, and when I'm talking about groups, I'm talking about columns going down, groups. They're also called families, and this is because as you go down a group, they have similar properties. So for instance, this first group here, and I'm not writing all the elements because that's going to take pretty much the whole class, but this first group is called the alkali, let's spell that wrong. So when I'm talking about this first group, I'm talking about all the way down. Hydrogen is not an alkali metal though. However, every other element in that group is. So lithium on down, I don't know what there is. Lithium, sodium, potassium, rubidium, cesium, all the way down. So those are all alkali metals. They all have similar properties. When we talk about valence electrons, they all have one valence electron. When we talk about their reactivity, they all have a similar reactivity. Okay, that's why they're in that group together. So what are we using this for in this chapter is if I give you any one of those elements, so if I say, okay, rubidium, what group is it in? You need to know, hey, it's in group 1, it's an alkali metal. So you need to know the common names and use the common names where appropriate. So the second group here, when I'm talking about the second group, if you look at the periodic table that I handed out or the one posted on Blackboard, notice there's a Roman numeral 2 and then an A, and then underneath it has a 2 in parentheses. That's group 2. Now it gives you both of those representations because some periodic tables use the Roman numeral form, other periodic tables will just put a 2 there. the reason I gave you this periodic table is because it has every possible option that you'll ever see on any other periodic table. Okay, so that way you won't get confused because you'll know, no matter what type of question, exactly what group it is. So this second group here is the alkaline earth metals. So that's their common name. So I'm talking beryllium, magnesium, calcium, strontium, barium, all the way down. All right, now this center group, I like to call it the D block, and you'll see why I'll be towards the end of this class. These are the transition metals, and that's already labeled actually on your periodic table that I handed out. Transition metals. So that's that whole section. A very large part of the periodic table. As we go down, so next we get to the boron. So this is group 13, or I think they say 3A. This does not have a special name. The reason that this group here does not have a special name is because these elements in this group don't have similar properties. So that's why they didn't give it a special name. You'll see why in a minute, because I'm about to show you where metals are, where nonmetals are, and where the semi-metals are. And this group has a combination of metals, semi-metals, nonmetals. So they have different properties. And that's the same reason why group 14 here also doesn't have a common name. Same with group 15 and group 16. Okay? So if I ask you what group is oxygen in, your answer would be group 16, because it doesn't have a common name. However, group 17 does. So group 17, fluorine, chlorine, bromine, and iodine, these are the halogens. And the very last group, the group everybody wants to be, are the noble gases. And I talk about the noble gases on the PowerPoints as an example because helium is a noble gas that a lot of people recognize because we put it in party balloons, right? So the common property that this group has is they're very unreactive. So all elements in this last group, in group 17, are very unreactive. Otherwise, we wouldn't put it in party balloons because party balloons are around flames. And if helium was a reactive element, we wouldn't want to put it around fire. So be able, given any of these elements, to tell me what group it's in. If it has a common group name, use that. If it does not, you would just use the number above that row. Okay? So what we're going to look at next is where the metals, nonmetals, and metalloids are. So I'll put those off to the side here. Metals, nonmetals, and then metalloids. Metalloids are also called semi-metals. So both terms are used, it just depends what text or person is describing them. So know that both of those words are used. So how do you know where all this stuff is? On the periodic table given to you, there's a bold line, a zigzag line, starting off to the side of boron and going down between aluminum and silicon, and then it keeps going down like this. Alright, so that zigzag line, it's there because it's separating the periodic table into metals, nonmetals, and metalloids. So what that means is everything to the left of that zigzag line, those are all going to be metals. So everything over here, most of the periodic table, with the exception of hydrogen. Hydrogen is a nonmetal. Everything to the right of that zigzag line are going to be the nonmetals. So, where are the metalloids? All the elements touching the zigzag line are the metalloids. okay? With the exception, you'll notice there's an exception for everything, just like hydrogen's over here, but it's a non-metal. Aluminum is the one element touching that zigzag line that is not a metalloid, it's actually a metal. But all the other elements touching it are metalloids. So, let's apply what we just learned. I'm going to put up some examples and we're going to classify them. So, got here. I'll just put the atomic symbols. So I have 1, 2, 3, 4, 5, 6 different elements here. We are going to classify them as metal, non-metal, metalloid, and give their group. So I'll put group here, and then we'll do the metal, non-metal portion here. So AS. AS is arsenic. So whoever finds it first, tell me how many protons it has, what its atomic number is, so other people can find it too. Arsenic. AS, yes. Okay, number 33. So it has 33 protons, that's its atomic number, but what is it? So what group is it in? Let's start with that. It doesn't have a special group name, so we would classify it 15. So it'd be group 15, or I would also accept 5A, either one. Roman numeral form. So what is it? Is it a metal, non-metal, or a metalloid? So that's a tricky one. It's to the right of the zigzag line, but notice it's touching the zigzag line. So since it's touching the zigzag line, it is a metalloid. Because it's touching, it's down here. It's not here, I think it's this next one. So it's touching the zigzag line. Since it's touching the zigzag line, it is a metalloid. Or a semi-metal. Both terms are mean the same thing. What about Kr? That's krypton. Krypton. So what is the atomic number of krypton, so everyone can find it? 36. So what group is krypton in? Does it have a special name? It's in this last column here. So we wouldn't want to say group 18 since it has a special name. Instead, we would call it, it's a noble gas. It's in this group along with helium, neon, argon, all noble gases. So now, based off this zigzag line, it's to the right of the zigzag line, so what is it? Metal, non-metal, or metalloid? It's a non-metal, yes. So now let's try fluorine. I even have it on the one I wrote up. There, so fluorine, what group is it in? Does it have a special name? We know it's in group 17 here. It's a halogen, yes. Because group 17, fluorine, chlorine, bromine, iodine, those are halogens. It is to the right of the zigzag line as well. So is it a metal, non-metal, or metalloid? Non-metal, just like krypton. Next example I have here is hydrogen. So hydrogen is that special guy. He's over here, but he doesn't belong there. So for the group, he's not an alkali metal, because it's not a metal. So we would have to say group 1 or 1A.
But why hydrogen is part of the group?
Because when we talk about valence electrons, hydrogen has one valence electron just like everybody else in this group. So there is a reason why he's there. He doesn't fit property-wise there, but he fits because he has the correct number of valence electrons. And he's a non-metal, yes. So he's the exception. That's why I like to use him as an example. Any other element in that group we would call an alkali metal though. Let's look for SR, strontium. What number is strontium? 38. So what group? So he's 38, he's in group 2. But the special name is alkaline earth.
Earth metal.
Yes, earth metal. And that kind of answered my next question, because its name has the word metal in it, so it is a metal. Now this last one's hard to find because it doesn't match with its common name. AU. When I find it on the periodic table, it is number 79. So what is AU? It is gold. So is gold in a special group? It is. It's a transition metal. Good. That tells you that it is a metal. And that's one that you would actually probably know just because gold, right? It's a metal. So you can make jewelry out of it, many other things. So, if you haven't watched the PowerPoints yet, I give more different examples of these. So if you get to that point, you can pause it and try to practice this on your own as well. See if you can identify the group and metal. Or if it's a metal, non-metal, or metalloid. All right. So at first, this can seem a little bit difficult, but the more that you practice this and the more you familiarize yourself with the periodic table, the easier it's going to become. So the first time you look at it, it's kind of like, whoa, there's so many. How do I figure this out? And it's just getting used to it. And we're using the periodic table for the rest of the semester, so by the end, you're really going to know where stuff's at. All right. Is there questions on this as I erase it? Oh, the picture. Erase one of the elements, but. What we're going to do next is we're still going to do the periodic table, but we're going to explore other areas of it. We're going to use it to figure out electron configurations. And the video will be posted too, so you can always look up these answers on there too. Don't want to erase my periodic table, I still need it. All right, so what we're going to do next is talk about quantum numbers. So I know the word quantum, this is physical chemistry. We're going to be using quantum numbers to represent elements on the periodic table. So what I mean by that, we're going to look at just two. One is called the principal quantum number. Scary looking title. But it's really not that scary because all that means, principal quantum number, is now we're looking at the rows going across on the periodic table. So if you look at your periodic table, you'll notice that there are numbers 1 through 7 on the side. Those numbers are your principal quantum numbers. Okay? So if I say, say I use oxygen as an example, and I say, what's the principal quantum number of oxygen? Okay, well, where is oxygen? It's right here. So what I'm asking for is what row is oxygen in? And if I follow it over, I see that it's in row 2. So that's its principal quantum number is 2. Okay, so it's a big word or a big phrase, but it does, all it means is what row is it in. Okay, so this is going to be our first piece of information when we start writing electron configurations. And what an electron configuration is it's describing where the electrons are. So remember in our picture of an atom, that simplified picture, we had the nucleus in the center, that positive center that had the protons and the neutrons in it, and then we had rings around the nucleus, and on those rings is where the electrons were. Remember I said electrons are hard to pinpoint because they're constantly moving. So what we're going to do with electron configuration is we're going to try to explain the probability or the area that those electrons are in. We're going to try to give that electron an address, so to speak. And we're going to do that by using a series of numbers and letters. So these orbits, these circles that I have where the electrons are on, these are the principal quantum numbers. So what I mean by that is this first circle would be n equal to 1. The second circle would be n equal to 2. The third would be n equal to 3. So what I mean by n is the symbol for principal quantum number. Okay, so if I say n equal to 1, I'm talking about an electron in the first row. If I say n equal to 2, I'm talking about an electron in the second row. N equal to 3, so on and so forth. So notice it goes all the way to 7 when we look at the main part of the periodic table. So down here, what is this guy, cesium? Yes. So in row 6 we have cesium. We're going to look at different periodic trends, but what I want you to know about cesium right now is cesium is the largest atom on the periodic table. Why? Look at its principal quantum number, it's 6. So the reason I'm not saying francium is the largest is francium's radioactive, so I'm ignoring him, okay? Other set of issues. Cesium is the largest because it has 6 rings. Okay, so I'd have to add 3 more rings. The more rings you add, the larger the atom's going to be. Okay, so we're going to see that atomic size increases as you go down because of the principal quantum number, because of how many rings that atom has. Okay? So this is our first piece of information. If you know the principal quantum number, what that tells you is you know which row to look in. But that's not good enough, right? We're only looking at the row, but we need to narrow it down further. So how we're going to do that is we're going to use our angular momentum quantum number. So we need another piece of information. So here's the first piece. The next will be angular momentum quantum number. Falling asleep on me. Sedatress. You make me feel like I'm boring. It's chemistry, it's got to be exciting.
Oh, I said about my submitted it all through my lab. Did you get it?
I don't know, I haven't looked since yesterday, so I probably did. But this angular momentum quantum number isn't an actual number, we're representing it with letters. So S, P, and D are the letters we're representing. So what we're doing with this number is, now that we know the row to look in, we're going to separate the periodic table into an S block, a D block, and a P block.
One of the questions on that quiz.
Oh, on the homework?
Yeah, on the homework.
Yep. So this is where you're going to get that information. So the S is this group here. So the alkali metals, the alkaline earth metals, that's the S block. That's the sub-level they're in. So how this is going to help us is if you know the principal quantum number, so say it's 3. Okay, well you know to look in this row. But if I say it's in the S block, now you've narrowed it down to just these 2.
And then jump to the next one.
Yep, this next one over here though, this whole section, this is the P block. So if you're in group 3, for instance, or row 3, this is the S's and the P's are these guys over here. Okay, so you're just narrowing down where on the periodic table to look. There's only one letter left, and that's the transition metals. And you might have heard me refer to this when I first drew it, the D block. I called it the B block. That's the transition metals, that entire section in the middle. So we're going to use numbers and letters to represent the electrons in an atom. And we're going to start with neutral atoms. Remember when we talked about neutral atoms, we said that for neutral, I spelled it right this time,
that the protons equal the electrons. Right? We need the protons and the electrons to be the same, cancel each other out. All right, so how are we going to do this? Well, first off, we need to talk a little bit about orbitals. All right, so an orbital is, it's not spelled orbital. See, I can't talk and write it at the same time. Oh, there we go. An orbital is a place where an electron resides. Okay? Each orbital can hold a max of 2 electrons. So orbital, that's a place where an electron is. Each orbital, 2 electrons max. So when I talk about this S block, we're going to look at the P block and we're going to look at the D block. What we're going to say is how many orbitals does each one have? And then we're going to look at how many electrons each of these sections can hold. Okay? So for the S, well, S just has 1 orbital. Okay, well, how many electrons, what's the max electrons it can have then? If each orbital can hold just 2 electrons and S just has 1. So how many electrons can the S have? It's just 2. Okay, how do I know that? Well, you can use the periodic table actually to figure that out. 1 electron, 2 electrons. That's it. So let's look at the P block. So count how many elements across are in the P block. 6. That's because the P block can only hold a max of 6 electrons. Okay, if it can have a max of 6 electrons, that means it has to have only 3 orbitals. Because I said each orbital, so if it has 3 orbitals, each orbital can only have 2 electrons in it. So 2, 4, 6.
So D block,
D block would have
10.
10, because if you count the elements on the periodic table, there's 10 across. Right? So how many orbitals is that? 5. Now, I'm not a very good artist, so I'm not going to draw what the orbitals look like, but if you would like to see pictures of them, refer to the PowerPoints. Okay? They actually have different shapes, so you can look at the shapes, but I'm going to stick with the numbers. So S, 1 orbital, 2 electrons. D, 5 orbitals, 10 electrons. P, 3 orbitals, 6 electrons. And if you ever forget how many electrons it can hold, just count how many groups are in each. Okay? So how does this help us? When we write the electron configurations, we're going to need to know the maximum amount of electrons that can fit in each. Okay? Because that's going to be a piece of information that's going to help point us to an area. So I'm going to erase this section, and I am going to give you an example of an electron configuration, and we'll explain what it looks like. Do you have a question?
You know, you said we'll use it later on down the line, so basically to help us pinpoint the symbol and stuff that we need quicker.
Yes.
Okay.
So we're going to look at neutral first, because that's easier than the ions. We haven't even talked about ions yet. So here, this would be an example of an electron configuration. So we're going to look at what these numbers and symbols mean. Well, these first numbers here, the big numbers, that's the principal quantum number. That's our N, the numbers on the side. Okay? The letters, those are our angular momentum quantum numbers, right? S's, P's. There's no D's in this example, but there can be. So the only number we haven't talked about then is this superscript here. These numbers, that's the number of electrons. That's why we needed to know the max electrons that can fit in each. So how do we use this? It's a map. It's a map of the periodic table showing us an element. So when we use a map, we always have to start at the start line and go all the way to the finish. So that's why it's always going to start with 1. It's saying, look in the first row. We're starting at hydrogen every time we describe an electron or an element. So the 1, we're starting here, it's saying you hit the S block first, right? Because if you start, this is my start line, I go to 1 and I hit the S block first. So I'm hitting hydrogen. Hydrogen would be 1s1. But it's not saying 1s1, it's saying 1s2. So it's saying go past hydrogen. Helium, even though it's over here, the reason it's here is because it's a noble gas. But for purposes of electron configuration, helium belongs right here. Because it's in the S block, it has 2 electrons. So what I'm saying is hydrogen, and if you look at the PowerPoints as well, I have an electron configuration periodic table in there that gives you what every element is, what its electron configuration is. So that might be useful to you as well. So if I'm talking about hydrogen, its electron configuration would be 1s1, because it's in period 1, it's in the S block, and it's the first element in the S block. Helium would be described as 1s2, because it's in period 1, it's in the S block, but it's the second one in the S block. So that superscript number is telling you how far to go in to that particular group. So 1s2 describes helium, but we need to keep going. This is telling me go further. So notice in period 1, I only have 2 elements, and I only hit the S block. So once I finish that row, I need to go to period 2. So that's why I see 2 next. What do I hit? S block first, always. And it says to go 2 in. So the second one in is beryllium. But then it tells me I'm not done. I keep going. I'm going to stay in period 2 this time.
But you're gonna go 4.
But I hit the P block next. So that's why it says 2P. I'm in the P block. And it's going to be carbon. So how do you know it's describing carbon? Because of this number here. It's saying go 4 in. 1, 2, 3, 4. So it's not carbon, it's oxygen. Carbon would have been 2P2. Because this number is saying how far into the P block to go. I think what you did is counted 4 total.
Yep.
So the 2s2 took care of these 2.
Now count 4.
Now count 4 into the P block. So this is talking, this whole thing just described a neutral atom of oxygen.
So once you get to the end, that's what it'll be.
Yes.
You always rely
So
on-
you really only need this piece of information to figure it out, because you say, okay, period 2, P block, 4th one in.
So if it was 3P6,
3P6, so 3 P block, and then the 6th one in. So whatever this guy is, argon.
Yep. Oh, how do you remember that?
So another way is for neutral atoms, since the protons equal the electrons, these numbers here I said represent the electrons, right? So let's add these together.
Add on.
4, 5, 6, 7, 8. So there's 8 electrons, and since it's neutral, there's 8 protons. So I'm talking about atomic number of 8, which is oxygen. And this is only useful if it's neutral, because then they equal each other. If we're talking about an ion with a charge on it, they'll no longer be equal. Okay, but we're going to start with just neutral atoms and get used to using this process first, and then we'll add the layer on later. All right, so now let's try to write one. So that described oxygen. Now I'm going to give you an element. Let's do sulfur. So S. We're going to write the electron configuration of sulfur. And when we write it, we have to start always in group 1. So it's always going to start as 1s. Okay, this is where our maxes are going to help us, because these will tell us, okay, if I need to go through that whole section, what is my electron count going to be? So for instance, 1s. Sulfur is in group 3. So we're going to have to describe all the way to period 3. So 1s, the number that's going to go here is a 2, because 2 is the max that fits in S, and I want to go all the way through that group. So 1s2, I want to go to helium. You're saying, okay, go to helium, but I want to keep going. So where do I hit next? What comes after 1s2? There's nothing else in period 1, so I'm going to have to go to period 2. What block do I hit first? S. What's the max that can fit in the S? 2. So what this is saying is go all the way to beryllium, but we want to keep on going. So we're still in period 2, but what block are we hitting?
P.
P. Is sulfur in the 2 Ps?
4.
No, is it in here?
Yes.
For 2 Ps? So this is period 2, this is the P block. Is sulfur one of these elements?
Yes.
I have boron, carbon, nitrogen, oxygen, fluorine, neon.
No, that's in 3.
No, it's in 3. So that means we need to go all the way through these Ps. So what's the maximum amount in P?
6.
6. So we're going to put 2P6 here. Because what we're saying is go all the way to neon, and then keep on going. So now I'm at neon.
So then you'll put 3.
Sorry, what was that?
Did you go back then?
And then go back.
After you get through with that?
Yep, then you
Go
go
back
to
down to
3P.
It's like you're reading a book.
Oh,
You go left to right until you get to the end of that line, and then you go to the next line.
So
So
then you'll say 3P4.
we'll get there, but notice at 2P6, I go to the 3s like you just said, but I don't hit P's first. What do I hit first?
S.
S, so I have to write 3S,
3S.
because I'm telling you, okay, once you get to the period 3, go through the S's. What?
3S.
2, because there's always 2. So I'm at magnesium. That's what guided element's here,
Mhm.
but I want to keep going. So I'm still in period 3, and I'm going to run out of room. It's my huge periodic table.
It's a 3D, it's a 3.
Yes, I'm just trying to rewrite it so that I have more room. Sorry. So I'm in 3. I went through the S's. Now I hit the P's.
4.
Sulfur. So which one in is it?
4.
It's going to be 3P4. So aluminum is 1, silicon would be number 2, phosphorus number 3, sulfur is number 4. So all of this is just, this is the only piece of information that really points to sulfur, this last piece. But when we write the electron
Why
configuration,
is
we
it
always start from the
that we're
beginning.
leaving out the D block in
We haven't hit it yet. You don't hit the D block until you get
that? But you're
to
passing through it.
period 4. There's nothing there though. So when I get to period 4, so if you look at your periodic table, that's when I'll hit the Ds. So I get to period 4, I hit the S block, and then I hit my first D. Scandium.
Got it.
But until I get to period
Okay.
4, I'm not hitting any Ds. They don't
Okay.
start until down there.
and I was looking at the
So then
top
it'd
here,
be a
and she
problem
said,
if we had,
Don't-
oh, go ahead. I'm sorry.
I was looking at the top up here, and she said,
Oh,
that's not, okay.
yeah, that's nothing. That's
Okay.
just telling you the group names.
Yeah.
So it could be, in that problem, well, not in that problem, of course, but if we did do 1, we would do 4,
So let me confuse you with
4D.
the Ds here. Now that we're understanding it, let me confuse you. Ds are always n minus 1, okay? What does that mean? N, that's the period that it's in. If it was n sub 0, that would be neutrons. But n, that's the principal quantum number, that's the periods that it's in.
Okay.
So let's do one where we have to go into that area. And then we'll end there because we're almost out of time. Let's do iron, 1, 2, 3, 4, 5. No, let's do manganese because those get funky. So we're going to describe the electron configuration of manganese, Mn. And that is number 25. So what we know is once we're done and we add these numbers, it should equal 25 over here. Because manganese is number 25, it's a neutral element, so the proton's equal to neutron. So start from the very beginning. We start with 1s. 1s2, we want to keep going. What do we hit next?
The second block, second period, 2, S2.
So 2s2 brings us to beryllium. Then we're still in period 2, but we hit the p's now. Do we want to go all the way through the 2 p's?
Yes, 6.
So 2p6.
Drop down to period 3.
What do we hit first? SP's or D's?
P. No, S. I'm sorry.
S. We always hit S's first.
S2.
So 3s2, brings us through that group.
Go over, third period, P, 3P. 6.
6. So the reason it's 6 is because we want to go all the way through those.
Ends right there. Fourth period,
Then we hit the 4th period.
D block.
We don't hit the D's first. What do we always hit first? S is first.
S.
We want to go, yeah, exactly. S's are lowest in energy, so it might help you think of it this way. S's are the lowest energy of the orbitals, so we always hit them first. Because you always want to fill from lowest to highest. So S's are always first.
2.
Or S2 brings us to, what are we, calcium? Okay, now we're hitting our D's for the first time.
4D.
And that's what everybody wants to do, but that's wrong. It is D, but it's not 4. So that's why I told you I'm about to confuse you. The D's are 1 less than the period they're in.
3.
So it's going to be 3D.
No, what?
This has to do with energy levels. So
Just leave me all the way.
is nothing, the reason behind why it's 3D, you don't need to know. I can explain it to you if you want me to confuse you further. So what you need to know about the D's is once you hit it, it's going to be 1 less than whatever period you're in.
Oh, I mean.
So if I'm in period 4, it's the 3Ds. If I'm in period 5, it's 4D. If I'm in period 6, it's 5D.
I'm one of those people that has to know why.
The reason behind? Next class period, we're going to do an orbital energy diagram. It's where we're going to basically draw this as a picture, and I can explain it then, because you'll see how the electrons are filling. We're even going to like draw the electrons as arrows and fill up a map.
So you subtract that from 1, that'll be 3D, and we're gonna go 5.
5, it's the 5th one in, so 3D5. So this piece of information tells you manganese. It's period 4, but since we're in the D's, it's 1 less, so that's why it's 3D.
And add all those up across the table, you should get 25.
Yes, if you add all of these, it should be equal to
12,
25.
13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25.
Because it's neutral, so the protons equal the electrons. And that is the number of protons of manganese.
Do you work with the whole numbers at each point, with the 1, 2, 3, 1, 2, 2, 2, 3, the periods? We ever use those for anything?
These? I mean, it's just the representations here.
Other than that, okay.
Other than that, not that I know of.
Gotcha.
So on Thursday, what we're going to do, whether you're here or watching the video, is just keep practicing this. So that's what we'll start with. We'll do some more examples, and then we're going to fill out an energy map. It's basically these letters in a picture form, and then look at ions and bring those into the mix.